This is one of Japan's most famous inventions, the bullet train.
Japan's Super Express, the Shinkansen.
Japan's cutting-edge $64 billion maglev bullet train was supposed to revolutionize travel, gliding at lightning speeds with zero friction. But now this futuristic marvel has hit a massive roadblock. Delays, political clashes, environmental concerns. Something is keeping this engineering masterpiece from becoming reality. With billions already poured into the project, why is Japan struggling to get it back on track? Could this setback threaten the future of high-speed travel? The truth behind the delay might be more shocking than anyone expected. Let's break it all down. Japan's race for the fastest train yet. Back in 1964, Japan introduced a revolutionary way to travel, the first ever Shinkansen, or bullet train. The launch of the Tokaido Shinkansen slashed travel time between Tokyo and Osaka, cutting the journey from 7 hours down to just 2.5. It was a breakthrough in transportation, proving that trains could compete with the booming aviation industry. Now Japan is on the verge of another revolution, one that could shrink that same journey to just 67 minutes. The secret? Magnetic levitation, better known as maglev. This cutting-edge technology has been around for decades, but Japan has refined it for the modern era. The country is building 2 new lines, one from Tokyo to Nagoya and another from Nagoya to Osaka. These trains won't run on traditional steel tracks. Instead, they'll hover 10 centimeters above them, using powerful magnetic forces to eliminate friction entirely. With speeds reaching up to 603 kilometers per hour, they will outpace even the fastest existing bullet trains. But this isn't just about speed. Japan has always used rail transport to shape its economy and infrastructure. The success of the Shinkansen 6 decades ago didn't just connect cities, it reshaped the country. When the first bullet train debuted, locomotives were seen as outdated, while air travel was the future. But Japan took a different path. In 1964, the Shinkansen reached speeds of 210 kilometers per hour, far exceeding the 150 kilometers per hour of conventional trains. It was a leap forward in technology, featuring a sleek, aerodynamic design that minimized air resistance and improved stability. Unlike traditional locomotives that relied on a single engine, these new trains were powered by multiple electric motors distributed along the cars, ensuring a smoother, more efficient ride. To maximize speed, Japan built dedicated high-speed tracks exclusively for the Shinkansen. These tracks were designed with minimal curves and inclines, allowing trains to maintain high speeds without frequent slowdowns. By avoiding the congestion of slower passenger and freight trains, the Shinkansen could operate with unmatched efficiency. The impact was immediate. The Tokaido Shinkansen drastically reduced travel times, making it easier than ever to move between major economic hubs. The Tokyo to Osaka trip, which once took 6 hours, was reduced to just 4. For the first time in Japan's history, rural communities and urban centers were seamlessly linked, allowing goods, services, and workers to move with unprecedented ease. The ripple effect was immense. Thousands of new jobs were created, industries flourished, and infrastructure rapidly expanded. Japan, still recovering from World War II, saw an economic boom so dramatic that historians would later call it the Japanese economic miracle. What started as a single 515-kilometer rail line in 1964 has since grown into a vast high-speed network spanning nearly 3,000 kilometers. With trains reaching speeds of up to 320 kilometers per hour, Japan has long been a global leader in high-speed rail technology. Countries across Europe and even the United States have tried to follow in its footsteps, using rail to stimulate economic growth. Meanwhile, China has built the world's largest high-speed rail network, pushing the limits of rail travel even further. Despite fierce competition, Japan's Shinkansen remains one of the safest, most efficient, and most reliable high-speed train systems in the world. It's a symbol of precision engineering, technological innovation, and passenger comfort. Naturally, the world is eager to see what comes next. And with the ambitious maglev project underway, Japan is once again aiming to redefine the future of transportation. But what makes Japan's maglev technology so groundbreaking? And can it truly revolutionize high-speed travel? Stay glued to your screen to find out. The technology behind maglev trains. Now let's explore what makes maglev trains so unique. There are two main types of maglev technology currently in use: electromagnetic suspension (EMS) and electrodynamic suspension (EDS). Each works differently, but both achieve the same remarkable effect, lifting trains off the ground and allowing them to glide at incredible speeds. EMS, or electromagnetic suspension, relies on powerful electromagnets embedded in both the train and the guideway, typically a monorail-like structure. When activated, these magnets generate a repelling force, lifting the train about a centimeter above the track. Unlike other systems, EMS ensures that the train remains levitated even when stationary, as long as the electromagnets are powered. This eliminates direct contact with the guideway, reducing wear and tear while allowing for sleek, aerodynamic designs. Though early designs faced concerns over stability, modern advancements have introduced highly effective control mechanisms to keep the train steady. On the other hand, EDS, or electrodynamic suspension, operates on a different principle. Instead of resting on a monorail, the train moves within a guideway that has walls on either side. These walls contain electromagnets that exert force in multiple directions, pushing the train upward while also pulling it toward the center. As a result, the train remains levitated at approximately 4 centimeters above the track, floating perfectly in place. The upper sections of the walls generate an additional stabilizing force, ensuring that the train stays aligned within the corridor. However, EDS comes with its own challenges. At lower speeds, the electromagnetic forces generated by the walls are not strong enough to keep the train airborne, meaning the train needs wheels or other support mechanisms until it gains enough momentum to lift off. Additionally, EDS systems create more drag due to the way their magnetic fields interact, slightly reducing their overall efficiency. Another major concern is electromagnetic interference. Without proper shielding, the strong magnetic fields could disrupt electronic devices such as hard drives, credit cards, or even pacemakers. While shielding solutions exist, they are costly to implement. A third, less developed maglev concept involves using permanent magnets that do not require external power to function. While this could theoretically reduce energy consumption, it remains an underexplored approach compared to EMS and EDS. Regardless of which suspension system is used, propulsion works in the same fundamental way. Unlike traditional trains that rely on engines, maglevs are propelled by coordinated magnetic fields. Instead of a conventional motor or external propulsion system, magnets along the track are carefully synchronized to activate at precise moments, pushing or pulling the train forward. This eliminates the need for a heavy onboard engine, allowing maglev trains to reach speeds that would otherwise be impractical. Just how fast can maglev trains go? Currently, operational maglev systems can reach speeds of around 500 kilometers per hour, faster than half the speed of a commercial jetliner. However, engineers believe the potential is far greater. If track layouts were perfectly straight and environmental factors were optimized, a maglev could theoretically travel as fast as magnets could be coordinated to push it forward. The fastest recorded maglev speed so far is 603 kilometers per hour, but this may only be the beginning. Beyond speed, maglev technology offers several additional advantages. Since the train floats above the track without direct contact, wear and tear on both the train and infrastructure is significantly reduced, meaning maintenance costs are lower compared to conventional rail systems. Maglev trains are also highly resistant to derailment due to their stabilizing mechanisms and are not limited by the width constraints that traditional rail cars face. Another key benefit is energy efficiency. Unlike conventional trains, maglevs do not burn fuel and produce minimal noise, since there is almost no friction between the train and the track. Their ability to handle steeper inclines also makes them ideal for regions with hilly terrain, allowing for smoother transitions between underground and above-ground stations. With these advantages, maglev trains are redefining high-speed rail travel, pushing the boundaries of transportation technology. But what if maglev trains could go even faster, pushing beyond current records to unimaginable speeds? Stay glued to your screen to find out. The evolution of maglev, Japan's high-speed breakthrough. The concept of maglev trains dates back to the early 1960s, but Japan has taken this technology to new heights by incorporating superconducting magnets. These advanced magnets serve a dual purpose, lifting the train off the track and propelling it forward with remarkable efficiency. But how exactly does this work? Maglev technology is built on fundamental magnetic principles. Like poles repel each other, while opposite poles attract. By harnessing these forces, maglev trains eliminate the need for wheels, significantly reducing friction and allowing for speeds that traditional rail systems simply cannot achieve. The Chuo Shinkansen, Japan's cutting-edge maglev train, is designed to reach speeds of 500 kilometers per hour. During a 2015 test run, it shattered records by reaching an astonishing 603 kilometers per hour, setting a new global benchmark. One of the key limitations of conventional bullet trains is the friction generated by their wheels. Even with streamlined designs and powerful engines, there's a physical limit to how fast a train can move while in contact with the tracks. To overcome this, Japanese engineers revisited an idea that has existed since the early 1900s: magnetic levitation. The Central Japan Railway Company has refined this concept by introducing superconducting magnets, which are cooled to an extreme temperature of -269 degrees centigrade. This cooling process enables the magnets to create a stronger, more stable levitation effect, allowing the train to hover higher above the guideway. However, maglev technology doesn't activate immediately. Initially, the train uses conventional rubber wheels to gain momentum. Once it reaches a speed of 150 kilometers per h, the superconducting magnets take over, lifting the train off its wheels and allowing it to glide friction-free. The system relies on two sets of electromagnetic coils embedded in the track. One set generates the levitation effect, while the other is responsible for propulsion, guiding the train forward at breathtaking speeds. The absence of wheels offers several significant advantages. With no physical contact between the train and the track, wear and tear are drastically minimized, making maintenance far less frequent and expensive compared to traditional rail systems. Furthermore, since the trains are controlled by the track rather than a driver, the risk of human error, collisions, or derailments is significantly reduced. The autonomous nature of maglev systems ensures smoother operations and enhanced safety. Another major benefit of maglev trains is their resilience to weather conditions. Unlike conventional railways, which can be disrupted by snow, rain, or extreme temperatures, maglev systems remain largely unaffected by environmental factors, ensuring reliable service year-round. However, implementing maglev technology comes with substantial financial challenges. Similar to the introduction of the first Shinkansen bullet trains in the 1960s, these new maglev systems require dedicated tracks to maintain high speeds and avoid congestion from slower trains. Constructing these specialized lines is a massive undertaking. The total cost of developing Japan's maglev routes is expected to exceed $64 billion, making it one of the most ambitious and expensive rail projects in history. The rise and struggles of maglev technology. As futuristic as it may seem, maglev technology has been in development for decades. The first commercial maglev system debuted in 1984 in the UK, operating on a short 600-meter route between Birmingham International Railway Station and Birmingham International Airport. This low-speed system ran for 11 years, providing a unique travel experience. However, frequent technical issues led to its closure in 1995, and it was ultimately replaced by a bus. It would take another 2 decades for the first high-speed maglev to become a reality. In 2004, China introduced the Shanghai maglev, designed by German engineers and capable of reaching 430 kilometers per h. The train covered the 30-kilometer journey from Shanghai's financial district to Pudong International Airport in just 8 minutes, compared to the 50-minute taxi ride. Despite its speed and efficiency, only 3 trains were built, each carrying 574 passengers and operating at 10-minute intervals. The project's cost, around $1.2 billion in 1995, nearly $2 billion today, reflected the enormous financial investment required. Germany had its own attempt at maglev technology with the Magnetbahn in Berlin, introduced in 1991. Designed for a short 1.6-kilometer track in a formerly divided part of the city, it reached speeds of 80 kilometers per h. However, with the Berlin Wall already gone, its necessity was questioned, and the system was shut down just a year later. Other low-speed maglev systems emerged over the years, including Japan's Linamo, which launched in 2005 and remains operational, covering a 9-kilometer route at 100 kilometers per h. South Korea developed the Incheon Airport maglev, a 6-kilometer system reaching speeds of 80 kilometers per h. Similarly, China introduced the Changsha maglev in Beijing's S1 line, both operating at low speeds. Despite these projects, maglev technology has struggled to gain widespread adoption. Ambitious maglev projects have frequently faced cancellations due to overwhelming costs. The Swiss Metro aimed to connect all Swiss cities within 15 minutes, using vacuum-sealed high-speed trains traveling over 500 kilometers per h, but its $24 billion price tag led to its abandonment. Germany's Munich maglev project, designed to connect the airport to the city center with a 38-kilometer track, was scrapped after costs nearly doubled. A Berlin to Hamburg line, approved in 1994, was abandoned in 2000 in favor of a slightly slower but more affordable train. Similar challenges emerged in Dusseldorf and Dortmund, where a planned maglev faced public backlash due to frequent stops diminishing its high-speed appeal. The United States has also seen its share of failed maglev proposals. A Baltimore to Washington, D.C. maglev was canceled in 2002 after residents opposed the demolition of neighborhoods to make way for the project. The estimated $4 billion cost, with half expected from private investors, further doomed its prospects. Pittsburgh attempted its own maglev system, but never secured funding. California had similar struggles, and Old Dominion University in Virginia scrapped its abandoned maglev tracks after wasting $16 million on the failed experiment. Several key factors have consistently hindered maglev projects: excessive costs, public resistance to route construction, and the reality that in many cases a conventional high-speed train serves the same purpose at a lower cost. One particularly damaging incident further eroded confidence in maglev technology: the Latham Transrapid collision in Germany. On September 22, 2006, during a routine test, a communication failure led to a maglev train crashing into a stationary maintenance vehicle at 162 kilometers per h. The accident killed 23 people and injured 10 others. While the failure was due to human error rather than a flaw in the technology, the incident devastated public trust, effectively ending Transrapid's maglev projects and setting the industry back decades. Despite these setbacks, recent developments offer a glimpse of hope for maglev technology. In 2021, China's CRRC unveiled the world's fastest train in Qingdao, capable of reaching 600 kilometers per h. China now plans to expand its maglev network, with new lines under construction between Shanghai and Hangzhou, as well as Chengdu and Chongqing. In Japan, the Chuo Shinkansen maglev line has been under construction since 2014. Designed to link Tokyo and Nagoya with a 285-kilometer track, this system aims to reach speeds of 505 kilometers per h. However, the project faces obstacles, including regulatory challenges and the risks of constructing underground tunnels in a seismically active region. Testing of the upgraded L0 series maglev is ongoing. Meanwhile, in the U.S., the Northeast Maglev project aims to connect Washington, D.C. and Baltimore, eventually extending to New York City. If successful, it could transform the 4-hour drive into a 1-hour maglev journey. However, the project still requires approvals from numerous agencies, and even in the best-case scenario, service wouldn't begin until 2030. Building maglev systems has proven to be one of the most difficult transportation challenges, with technical hurdles, astronomical costs, and public opposition making progress slow. Even in countries where maglev has the best chance of thriving, like China and Japan, conventional high-speed rail remains the preferred choice due to its lower costs and practicality. However, if new projects like the Chuo Shinkansen and Qingdao maglev prove successful, they may reshape perceptions of the technology. Until then, maglev remains a futuristic dream, struggling to find its place in modern transportation. But what is stopping maglev trains from dominating modern transportation despite their futuristic promise? Stay tuned as we uncover the challenges. The maglev dream, a project stuck in limbo. Looking back to 2009, when Japan embarked on an ambitious journey to revolutionize transportation with its maglev project. The goal was clear: create the world's fastest commercial train, linking Tokyo and Nagoya in just 40 minutes, eventually extending to Osaka. Construction began, and everything seemed set for a grand opening in 2027. But now that deadline is long gone. The first phase of the maglev line, spanning 287 kilometers, is now delayed until at least 2034, with the second phase to Osaka pushed beyond 2037. At the heart of this decade-long setback lies a mere 9-kilometer section in Shizuoka Prefecture. This mountainous region, home to the Oi River, has been a major point of contention. Governor Haita Kawakatsu opposed the tunnel construction beneath the southern Japanese Alps, fearing it could disrupt the Oi River's water flow. This isn't just any river, it's a lifeline for the region. Shizuoka produces 25,200 tons of tea annually, accounting for 36% of Japan's total output. Any change in water levels could devastate tea production and threaten hydroelectric power from the river's dams. JR Central promised to pump water back into the river, but internal reports admitted that losses could still reach 2 metric tons per second. Adding to the tension, Shizuoka is the only prefecture along the route without a maglev station. Already overwhelmed by tourism, it has little incentive to approve a project that brings no direct benefits. The stalemate between JR Central and Kawakatsu lasted for years, until March 2024, when the railway company officially announced they could not meet the 2027 deadline. Days later, Kawakatsu made an ill-advised remark, belittling farmers and vendors, and triggering public outrage. By April, he was forced to resign. In September, the new government approved a preliminary boring survey, signaling a shift in stance. But even with this breakthrough, obstacles remain. In Aichi Prefecture, soft ground conditions have delayed tunnel completion by over 5 years, pushing the timeline to at least 2030. The domino effect of these delays continues to spread, making the project's future uncertain. But what do you think? Will Japan's maglev project ever overcome its endless delays and political battles? We'd love to hear your thoughts. Don't forget to subscribe.